Good afternoon, Space Cadets. Thanks for tuning in to another Planetarium live stream. My name is Patrick Hess. I'm the Planetarium Specialist at Union Station, and I'm very excited to have you joining us for yet another Monday evening deep dive stream, where today we'll be talking all about space telescopes. If you're joining us for the first time, welcome. Thanks for tuning in, and thanks for supporting the Planetarium and Union Station in this way. If you enjoyed the stream, please tell your friends. And if you're a returning watcher, then thanks for tuning back in. Just as a reminder, this is an open and interactive live stream, so if you have any questions or comments, be sure to throw those in, and I will try to answer them as they come, or just give shout-outs and comments. So please feel free to comment. By the way, if you hear any random noises like kissing sounds, that would be my parrot just in the other end of the room. So that is not someone randomly making kissing sounds off screen, although that would make for an interesting live stream. But anyway, we are going to jump in because I am very aware there is a Chiefs game tonight, and I'm guessing some of our watchers may be interested in that as well. I may be providing some score updates throughout the stream, don't you worry. But we are going to keep this, hopefully keep this a bit short and sweet. I know I always go over with my live streams, but you guys seem to enjoy them. Before we started, though, I did just want to do a little bit of housekeeping because there was a question that was asked last week during last week's stream, which was all about TV astronomy or TV shows that deal with astronomy, where we talked about a lot of fun television universes and how they related to space science. And we had a question related to Star Trek, which I talked about a little bit. And this question was from Casey, who asked about hive minds or hive artificial intelligence like the Borg from Star Trek The Next Generation. And at the time, I couldn't totally answer that. I did a little bit of research, didn't have time to do a ton, but just to kind of answer your question, Casey, there are a couple different examples of artificial intelligences that do use ideas kind of like the Borg. There's something called swarm AI, which uses a number of different processors all working together in sort of a big sort of hive swarm. And then I also wanted to bring up that there's a concept called superorganisms, which is more of a biology thing that biologists use to describe really large groups of animals. For example, like termites or bees or even coral that all exist symbiotically together and sometimes move together and cannot exist alone. So all these species, the animals, are generally considered to not really survive on their own that well, and they sort of exist as a collective or a hive. So some examples of the real world where sort of Borg-y type things existing. So Casey, if you're watching, hopefully that kind of answers your question. Getting a couple comments already. We've got a couple of our longtime watchers who I recognize. We've got Eric chiming in saying Yahoo. Tammy says, hi again from Iowa. Hello, Tammy and Eric. Thanks again for watching. And thanks for continuing to support us in our live streams. And one last little reminder, although we love for you to join us during these live streams, and we're planning on continuing them for quite some time, just a reminder that Union Station and the Planetarium are open to the public 5 days a week from Wednesday through Sunday. And if you'd like to come see us in person, if you feel comfortable, please consider joining us and buying a ticket online in advance. That's another great way, of course, to support Union Station. You can also purchase a membership, which gets you a lot of great benefits to the Science Center and the Planetarium, and discounted tickets to our traveling exhibitions like Dinosaur Road Trip. So come visit us sometime if you feel comfortable. If not, or if you do and still want to watch these live streams, that's of course welcome. And we're going to jump right in to today's topic, which is all about space telescopes. I'm just checking the game. It looks like no score updates. I don't think it's officially started. I think it starts officially at 6:05. Oh, Sandy's chiming in saying hello from Olathe. Awesome. Thanks for watching, Sandy. That's close to where I grew up, around Lenexa. All right, so we're going to jump into a discussion about space telescopes. And I wanted to talk a little bit about, first of all, why do we put telescopes in space? I mean, we got telescopes here on Earth. You can go to an observatory to look at a ground-based telescope, or you can set your own telescope up. In fact, if you have a telescope gathering dust at home and are curious about how to set it up, I'd encourage you to re-watch one of our past live streams, which was on May 6th of this year, because I set up a telescope live in my living room, and I talked about how to set up telescopes and how to use them. And as another reminder, you can re-watch any of our past live streams on our YouTube channel. Just search YouTube for Kansas City Planetarium or Gottlieb Planetarium, and that'll pop up. You can re-watch any of those streams. So, like I've been saying, you can, of course, observe from here on Earth. But why there are still a lot of reasons why we want to observe from space, and we'll talk a little bit about them when I dive into different types of space telescopes. But let's first talk about what are some reasons why we would not want to observe from space? Why would we prefer to observe from Earth? Well, first of all, there are some limitations to space telescopes. They can't be too big because, well, we don't have very big spaceships yet. Our spacecraft have limited capacities, and whatever you send to space has to fit in that spacecraft. It has to be small enough to fit inside the rocket and light enough for us to get to orbit with that amount of rocket fuel that we can fit on the rocket. And the other limitation is that there is limited repairability. So when I send a telescope up to space, depending on where we send it to space, which we'll talk about later, it could be really difficult to repair. There are some telescopes that we're lucky that we have been able to repair, like the Hubble telescope, which we'll touch on later. But many telescopes we'll send very far away from Earth, so far away that we could never possibly hope to send a crewed mission to fix these telescopes. So we can make much bigger telescopes on Earth, and it's a lot easier to fix them. But there are definitely some reasons why we would want to send telescopes to space. Now, there are two main different types of space telescopes, or space observatories as we call them. There are space observing telescopes, and then there are Earth observing telescopes, or Earth observing satellites. Now, Earth observing satellites are telescopes pointed back to Earth. And those are mostly operated by NOAA. That's the National Oceanic and Atmospheric Administration, at least here in the States. And we're not going to touch on those too much because that's not really astronomy. But those are really important. Of course, these satellites and telescopes observe the Earth and observe weather patterns and ocean patterns and help us to learn about things like climate change. But today we're going to focus on space observing telescopes. Telescopes and satellites in space that are pointing out towards space. We sort of separate telescopes by the types of wavelengths that they are able to image. And we've talked about wavelengths in the past during a number of our previous live streams. I believe we talked about them during our Stellar Evolution live stream back in April 15th. My bird is feeling very, very kissy. I don't know if you can hear these sounds on the live stream, but she's being very adorable. Yes. Maybe she'll make an appearance later on in the stream. But it's very distracting. You know what? Let's take a little break. Let's see if Phoebe will join us for a minute. Come here. Come on. She's a little bit wet since she just took a shower right before the stream. Do you want to hang out for the beginning of the stream? This is Phoebe, by the way, in case anybody didn't meet her before. Oop, she just sprayed my computer. That's fine. So telescopes observe in different wavelengths. Wavelengths are how we separate different types of light. So light, or electromagnetic radiation, comes in a variety of wavelengths. And we can see a certain amount of wavelengths. We call that the visible light spectrum. But wavelengths in longer or shorter frequencies are not visible to the naked eye, and so we need special instruments to be able to observe them. And so different types of telescopes have been designed to observe different types of wavelengths, and there are different reasons why we might want to observe different wavelengths, and we'll talk about those. So let's start on one end of the spectrum. We'll start on the short wavelength end of the spectrum, and we're going to talk a little bit about gamma rays. So gamma rays are blocked by the Earth's atmosphere, which is one reason why we definitely want a space telescope to observe them. But not only are they blocked by the Earth's atmosphere, these gamma rays, but they're some of the hardest to focus on. Astronomers even have to rely on special techniques and tricks, like actually detecting shadows of gamma rays instead of the rays themselves, using masks on their detectors. So they're really, really difficult to image. Gamma rays and gamma ray bursts are some of the most mysterious astronomical phenomenon. A gamma ray burst is an extremely high energy burst that's observed usually in distant galaxies, and they're some of the brightest and most energetic electromagnetic events known to occur in the universe. And they can last anywhere from 10 milliseconds to several hours. Many of them are very short, though. And scientists think they are probably released during superluminous supernova explosions, which usually create black holes. So these gamma ray bursts are thought to come from the creation of black holes. They were actually, interestingly, they were first detected by the Vela satellite in 1967, which were actually designed to detect covert nuclear weapons tests. They just happened to detect the first gamma ray bursts back then. And one example of a telescope, a space telescope, is the Swift Space Telescope. And in order to capture these really short-lived gamma ray bursts, the Swift telescope was designed to capture or image half of the entire sky at any given time. So instead of looking at a small region of the sky, it's looking at the entire half of the sky. And that way, if something pops up super quickly, we don't have to turn the telescope to point towards it. We can just kind of capture it when it happens. So that's kind of a cool type of telescope, just sort of looking at. It's kind of weird because you always think of telescopes as zooming in on something, but the Swift telescope is designed to just sort of be as wide as possible, but we still consider it a telescope. So moving up the spectrum, let's talk about X-rays, another type of electromagnetic radiation that telescopes image. And we also need space telescopes to image X-rays because X-rays are blocked by the Earth's atmosphere as well, so space observation is required. There are a number of astronomical and astrophysical objects that emit X-rays, like galaxy clusters, black holes, and mostly in galactic nuclei, so like the black hole at the center of our galaxy, as well as supernova remnants. X-rays pose a really particular challenge because they are so small and energetic that they actually don't bounce off of mirrors. They actually pass through mirrors, which is kind of annoying when it comes to light. Usually we prefer light to bounce off of mirrors. That's what we're used to. But X-rays just go straight through mirrors. So to focus X-rays, space telescopes actually require really long focal lengths. So in other words, the mirror and the detector have to be really far apart, in some cases several meters apart. One example of a space telescope is the Nustar space telescope, which was launched relatively recently. And this, now when we send a telescope to space, remember we're limited by how big it can be. So a telescope like this might be really hard to launch to space, but scientists and engineers have developed telescopes that actually are able to expand when they get to space. So this telescope started small with the mirror and detectors close together, but then they expanded to sort of stretch out like this, several meters long. So that is an X-ray telescope. Continuing up the spectrum, we have, don't chew on my glasses, we have ultraviolet radiation, which is a little bit close to visible light. Earth's atmosphere absorbs a lot of ultraviolet light, so again, ultraviolet astronomy is preferred to be done in space. One recent example of an ultraviolet telescope is the Galaxy Evolution Explorer, or GALEX. Scientists and astronomers really like their acronyms to sound cool. This was launched in 2003, and its goal was to observe the history of star formation in our universe. During its 10-year mission, before it shut down operations in 2013, it had observed over 500 million galaxies, going all the way back to when our universe was only about 3 billion years old, which is pretty young, all things considered. So that's ultraviolet radiation. Now, ultraviolet radiation and light can also be detected by some visible light spectrum telescopes, and there are some telescopes that are sort of jacks of all trades that can detect a lot of different forms of light. And on that topic, we are going to move on to the visible light spectrum, what humans can see. Before we do that, though, I'm going to check the comments. Oh, Lauren's commenting and saying hello to Phoebe. Lauren says hello, Phoebe. And Phoebe says hello back. She's doing a lot of beak grinding, which means that she's feeling a little tired. Do you want to go back? Let's send her back to her cage. Bye. All right, there we go, a little Phoebe cameo for you. So let's talk about visible light. So visible light is great. It can pass through the atmosphere, which is why it's really easy to observe visible astronomy here on Earth with ground-based telescopes. And that's also why astronomy is pretty much as old as humanity. Today there are tens of thousands, maybe even hundreds of thousands of ground-based telescopes and observatories. We usually call this optical astronomy. And although this is so prolific, there are some limits to ground-based astronomy. Of course, there's light pollution. You know, whenever we're close to the city, there are man-made light sources that block a lot of the views of the stars. And then there's also atmospheric interference. So visible light is really prone to being messed up by the atmosphere. We've talked about this during our Star Tour streams, where I talk about how stars twinkle, and that twinkling is because our atmosphere is causing that light to sort of wobble as it passes through our atmosphere. Now, there are ways to account for this wobble using a technique called adaptive optics. So a ground-based telescope can measure basically the shape of the wobble using this sensor, and then it can have another instrument that basically wobbles a mirror. We call these soft mirrors, and it sort of matches the wobbles to sort of unwobble the image, and then what we end up having is actually a pretty clear image from ground with very little atmospheric distortion. So again, there are ways to account for these problems with ground-based astronomy. But there are still, you know, this adaptive optics is still a pretty delicate technique and can be very expensive. And so it's still ideal to send telescopes to space. We have sent a number of visible light telescopes to space, and one of the most famous examples, of course, was the Hubble Space Telescope, which I have added to Space Engine. This is kind of cool. You can add telescopes to Space Engine, so I've added the Hubble here. And this, I believe, is its current location there. Let's see. It looks like it's about to fly over the equator there, right to the west of Mexico. But the Hubble Space Telescope was launched by NASA for the Space Shuttle in 1990. And it has been exploring and observing ever since. This telescope has a 6-foot wide mirror, and it is a pretty incredible piece of technology. Let's adjust that again. Now, when we first launched Hubble, it actually wasn't very good. There was an issue with Hubble that, let's see... there we go. There was an issue with Hubble that the mirror didn't quite work correctly when we launched it at first, but luckily, because Hubble again was in low Earth orbit, we were able to service it. So in 1993, a shuttle mission went to the Hubble Space Telescope and actually fixed the optics, and you can see sort of the before and after here. And so we're very lucky that we were able to actually get to the Hubble Space Telescope and fix those problems. Now, there is a really great website called hubblesite.org where you can and actually, Hubble just celebrated its 30th birthday recently, and you can look at all the news or all the images and videos that Hubble has captured over the years. So hubblesite.org is a really great resource if you want to learn more about the Hubble. I did go ahead and take the liberty to compile some of my favorite pictures from the Hubble Space Telescope. Since it is visible light, we have some spectacular imagery. These are the pillars of creation where new stars are being born. We also have the Horsehead Nebula here. I believe this is actually an infrared light. Again, the Hubble Space Telescope can capture a lot of different wavelengths of light. This is the Cat's Eye Nebula, a very, very cool nebula here. And the Sombrero Galaxy, one of my favorite Messier objects. I believe I mentioned that during my Messier live stream, which you can rewatch and find on April 22nd. Wow, we've been doing these a long time. Oh, and my favorite deep space object, personally, the Orion Nebula here, imaged by Hubble. Pretty spectacular. A lot of great images. Perhaps one of the most important images captured by Hubble, though, is actually the background to our live stream. This is the Hubble Ultra Deep Field. And this is basically a super zoomed in image of the night sky that was captured over the course of many, many nights, capturing a long time, a very long exposure of light. So basically what we're looking at here is an ultra zoomed in picture of the night sky looking back billions of years. So some of the galaxies in this photo are 13 billion years old and date back to almost right after the formation of our universe. So this was a pretty groundbreaking photograph that just, again, revealed the scale of our universe, and we are now able to peer so far back in time that it's pretty incredible. Now, another really important ground-based sorry, not ground-based. Another important visible light-based space telescope was the Kepler Space Telescope. And I wanted to share this with you guys because NASA has a really great resource about Kepler and its mission. Now, the Kepler Space Telescope, its primary mission is to look for exoplanets. So this telescope was launched in 2009, and it was looking for planets orbiting distant stars. And we can learn about the Kepler mission by going to exoplanets.nasa.gov, which I will share with you here of what it looks like. And this is a really great free NASA resource that's showing us the Kepler imagery. So every dot here is a star that Kepler and a couple other satellite missions like TESS, which is the Transiting Exoplanet something. I forget the exact acronym, but basically another telescope to explore exoplanets. And every dot here you see is a star with a known planetary system. And you can see there's this cone here. This was the primary Kepler mission. Kepler actually only looked at a very small portion of the sky. And all of these missions combined really just look at a small portion of our galaxy. But this website is really cool because this is obviously the space view showing us in 3D space. But we can also go to the Earth view, and it's going to zoom into Earth and let us choose a location, which I'll just pick as around Kansas City, and it'll land us on Earth. And it'll basically show us a view from Earth of these exoplanets. And if I move around here, you can see, oh, there's the Kepler region. So Kepler was imaging just a pretty small region of the sky. And inside this region, it found thousands of exoplanets. So thousands of planets orbiting distant stars. And it's really cool in this website. You can click one of these stars and you can actually zoom in on it, and it'll actually show you the planetary system. So we can see Kepler 1106 along with 1106b, and it'll even show you sort of an artistic rendering of what this planet might be like. And it'll tell you a little bit of information like this planet is a potentially rocky world larger than Earth. So really awesome and fun website to explore. So I'd encourage you to check that out for sure. And again, that is, what did I say it was? Oh, I lost the, let's see if I can get it back. Nope. I believe it's exoplanets.nasa.gov. So really cool. Their series is called Eyes On. So if you Google search for NASA Eyes On, you can find all this information, and all these cool interactive visualizations that NASA's put together for free. Very neat. One other cool satellite I wanted to talk to you guys about, visible light satellite, is the Stereo satellite. And this was a pair of satellites, one of which we've lost contact with. These are two identical satellites, one orbiting behind the Earth and one orbiting ahead of the Earth in a heliocentric orbit. So this is going around the sun like the Earth is. And these two satellites are spaced apart so that they're able to both look at the sun together and actually get a 3D stereoscopic image of the sun, which is really cool and useful for imaging things like coronal mass ejections, seeing those from a stereoscopic view. Very cool. Unfortunately, one of these telescopes we did lose connection with, but the other one is still, we are still communicating with. So, but pretty neat that we can send multiple telescopes out to space and get 3D images from telescopes by spacing them out like a giant pair of eyeballs. So that is visible telescopes. Let me jump back into the comments and check in. We've got an update from the game, by the way. I just realized I had to refresh my stream, and it's looking like the Kansas City Chiefs have scored 3 points. Congrats to the Chiefs. It looks like we're in the first quarter with 7 minutes remaining, so we are up by 3. Go Chiefs! All right, so Eric is asking or saying, I might have missed it, but is the X-ray telescope the one they use to find black holes? Yes, so the X-rays are often emitted from black holes, especially supermassive black holes at the center of galaxies. So we do use X-ray imagery to photograph black holes like that. Michelle chimed in saying that Michelle was loving my sidekick Phoebe. Somebody liked you, Phoebe, that's nice. No, Phoebe's pretty great. She's just a baby bird. Cynthia says, Chiefs! I assume in reaction to that score. And then Marcy says, thanks for the Chiefs score, and great info, Patrick. You're welcome, Marcy. Thanks for tuning in. I'm glad you're watching. All right, so let's continue right along past the visible light spectrum down to the longer wavelengths over to infrared. And just want to make sure didn't miss anything. Okay, yep. All right, so we're going to go on to infrared imagery. So infrared imagery is interesting because, first of all, some infrared radiation actually does make it through the Earth's atmosphere, so we can do some infrared observing from Earth, but some of the longer wavelengths of infrared radiation are blocked. But the biggest challenge with infrared imagery is that everything emits infrared light. Everything. The atmosphere, telescopes, even the infrared detectors themselves emit infrared light. You emit infrared light. We usually refer to infrared light as heat, or body heat, for example. So this is really challenging if we're trying to image infrared light on Earth, of course. So this is definitely one of the examples where imaging from space is super helpful because space is a bit chillier than Earth, a lot less heat in space. So it's an ideal location for an infrared telescope. In fact, many infrared telescopes are actually very far away, further away than Earth. And we'll talk about that when I go through some examples. For example, let's talk about the Spitzer space telescope, which we can go back to our NASA EYES program. And this is really cool. So when you click on these and double click on them, and you can actually zoom in, and this will show you some imagery. This is free software. You don't need to use a program like Space Engine. This has it all built in, and NASA provided this. So you do have to download and install it, but this is their Eyes On visualization software. but a really, really slick software that has information about their telescopes. You can click this button to read all about them in depth. And then there's a lot of other interactive features here. This is basically like a pretty slick sort of free planetarium software. So I'd encourage you to check this out if you want. It is available for Windows. I don't know if it's available for Mac. I would think so, but don't quote me on that. Maybe we can confirm that in the comments. Anyway, so the Spitzer Space Telescope is in a heliocentric Earth-trailing orbit, just like the stereo telescopes I was telling you about. And again, the reason for this is we want it as far away from Earth as possible. So even like the Hubble Space Telescope in low Earth orbit is around a lot of infrared radiation, even coming from the Earth. So we want to get our infrared telescopes very far away from the Earth. Some other examples is the Herschel Space Observatory, launched by the European Space Agency in 2009. There is the Wide Field Infrared Survey Explorer, or WISE, launched in 2009. And WISE was in the news this summer because WISE was the observatory that detected the comet Neowise. And this comet was gracing our heavens earlier this year in the summertime, and there's some really spectacular views of it. If you got a chance to see Neowise, it was visible to the naked eye, but let me know in the comments if you got to see Neowise. It was a pretty spectacular comet that was discovered by the WISE telescope. There is the Stratospheric Observatory for Infrared Astronomy, or SOFIA. Although this is technically a high-altitude satellite, it's actually strapped onto the top of a 747, and they use it to fly very close to the edge of the atmosphere, but I guess technically not in space, but I just wanted to mention that. And then the most notable infrared space telescope is one that has not launched yet, and it is the James Webb Space Telescope. And the James Webb Space Telescope is kind of the whole reason why I chose this topic for today's stream, because this telescope was named after James E. Webb, who was the second administrator for NASA, and his birthday was on October 7th. So we're celebrating James Webb's birthday by talking about space telescopes. And let's talk a little bit about this James Webb Space Telescope, which many talk about as being sort of a successor to Hubble, which is an interesting way to think about it, and I'll talk about why that may or may not be totally accurate. Now, the James Webb Space Telescope is very large, as you can see there. These people are very tiny and about 6 feet tall. Ooh. I got to get a good thumbnail for when I post this to YouTube like that. Okay, there's my thumbnail. So the James Webb Space Telescope is very large. It has about a 21-foot diameter in total. Well, you'll notice it's a bit different than the Hubble, so it doesn't have one round. It doesn't have one round mirror. It has segmented mirror, so it has hexagonal mirror segments that actually are able to fold up so that they can fit it inside of a spaceship to take to space. Now, this spacecraft, this telescope, has had a bit of a rocky history. Right now, it's scheduled for launch in October of 2021, about a year from now. It was originally planned for launch in 2007. So it's had a couple delays. Now, it was completely redesigned in 2005, so that set it back quite a bit. But construction was completed in 2016, which is a little bit of time ago, about 5 years ago. Since then, there's been a lot of testing, which has delayed it, and there have been some administrative and political delays. And then, of course, with the lovely year that is 2020, there are some other human delays that are causing that. So right now, we are scheduling an October 2021 launch for the James Webb Space Telescope. Now, unlike the Hubble, this telescope will primarily focus on the infrared spectrum. So Hubble had a lot of instruments, but all those amazing photos were taken by the visible imagery imagers on the Hubble. So unfortunately, the James Webb Space Telescope will not be providing sort of cool space pictures. Don't worry, Hubble's still up there, and it's still providing great pictures for us. But James Webb is going to be even cooler because it's going to hopefully find some pretty awesome science for us. Now, it is designed to observe objects that are extremely distant. Far more distant than even the most distant photographs taken by the Hubble, like the ultra deep field. So its infrared imagery will be able to peer way back to the very beginning of our universe. Now, because it is looking at that infrared radiation, we are going to send it very far away. We're actually going to have it parked at Lagrange point 2, or L2. And a Lagrange point is just a point in a gravitational field that's sort of balanced. So if you look here, this is the gravitational field sort of map or topography between the Earth and the Sun. So there are points in this orbital path that are sort of like little, I guess you could say, eddies, where the little areas inside the swirl of gravity that are balanced between 2 points. So, and you can see L2 is kind of sort of on the edge of Earth's gravitational field and sort of on the edge of the influence from the sun. So this is a spot where basically we're going to park the James Webb Space Telescope, or we may have it sort of orbit that spot. And it will be able to stay there with very minimal fuel, so it won't have to sort of move itself around to stay in that spot. And it will be very far away from the Earth. Of course, this image is not to scale, but it'll be far away from the Earth, away from all the heat, so it'll be able to get that imagery pretty awesomely. Now, because it's so far away, it will definitely not be serviceable like the Hubble Space Telescope, unfortunately. So we better get it right on our first launch. We definitely don't want another 1993 Hubble issue. So that is infrared imagery, and just a couple more wavelengths to take a look at. Let's see, checking the score. No score updates so far. We got 4 minutes left in the first quarter, still 3-0 with Chiefs on top. All right, so let's move on past infrared, continuing to longer wavelengths. Let's talk about microwaves. And I'm not talking about heating up a bag of popcorn. So a microwave is a wavelength of light, and it is a wavelength of light longer than infrared radiation, and similar to many other forms of non-visible light, the Earth's atmosphere blocks most of the microwave band of light. Now, the entire sky is a source of microwaves in every single direction. So when we study microwaves, we generally look at the entire sky. We're not just peering into one sort of section of the sky. Now, we refer to this sort of envelope of microwaves all around us as the cosmic microwave background, or CMB for short, and it looks a little bit like this. So this is a picture of microwaves enveloping our universe. Now, these microwaves are thought to be the remnants of the Big Bang, so the act that created our universe. At the beginning of our universe, all matter that existed was compressed into one very, very tiny and very, very hot ball. And as this ball expanded outwards, the universe cooled, and eventually all this matter and mass coalesced to form stars and planets. But it's continued to expand and it's continued to cool, and today, on average, the universe is about 3 degrees above absolute zero, which is pretty chilly. But when we measure this cosmic microwave background, the small amount of variation we see is this. This image basically is just showing us sort of the distribution of heat in our universe. There are a number of telescopes that are exploring the cosmic microwave background. There's the Cosmic Background Explorer, launched in 1989. There is the Odin Telescope, which was actually launched by Sweden in 2001. Kind of cool. A country we don't often hear about when we're talking about astronomy and space exploration. We have the WMAP, or the Wilkinson Microwave Anisotropy Probe, and then the Planck Observatory, launched by the European Space Agency in 2009. So a couple different observatories looking at the cosmic microwave background. Now, the last wavelength of light we'll talk about is radio waves. That's right, radio waves are a type of light. Radio waves can make it through the Earth's atmosphere without significant obstacles, and they can also escape the Earth's atmosphere without significant obstacles. And that's why when we think about, and this is a bit of a change of subject, but when we think about our messages to space, the signals that aliens, if they existed, the kind of signals they would receive, the first things they would hear would be our radio waves, the first radio waves we ever created, because that was the first sort of form of mass communication, when we sort of invented the ability to send radio waves through the air and around the world. So some of these early radio waves dating back decades may be the first things to be detected, because they, again, that electromagnetic radiation was able to escape the Earth's atmosphere. So because radio waves can pass through the atmosphere, in principle, we don't necessarily need to put a radio telescope in space. And there are many radio telescopes here on Earth. In fact, they're one of the most common types of telescopes, or telescope arrays. These types of telescopes on Earth often don't appear as you might imagine. They often look like satellite dishes on Earth. And again, they are just capturing radio waves in the same way that the satellite dish on your roof may capture TV signals in the same form of waves. And the same form of electromagnetic radiation. So those are telescopes, even though they may not look like kind of what you imagine a telescope to look like. There are some reasons why we might want to send a radio telescope to space, and that is because we can actually combine radio telescope signals. So this is a technique called interferometry, and it's a technique that astronomers use by basically combining telescopes either around the world, or in a better case, on the Earth and away from the Earth out in space. And we can combine data from 2 separate telescopes, and the further spaced out apart they are, the increased resolution we can get. So if I have a telescope in space, a radio telescope in space, and a ground-based radio telescope, my resolution of my radio imagery I can detect can be increased theoretically exponentially. So I can create a giant telescope with an array of telescopes out in space. We can theoretically create a telescope imaging system the size of the entire planet. In fact, we have actually done that. Now, we've only ever sent 3 radio telescopes to space. There was the Zond 3 radio telescope sent by the Soviet Union in 1965. There was the Highly Advanced Laboratory for Communications and Astronomy, or HALCA, sent by Japan in 1997. And then there was Spectre R, which is a Russian radio telescope sent in 2011. So it's not as common, and most radio telescopes are here on Earth. Some examples, like the very creatively named VLA, or Very Large Array telescope, which is a very large array of radio telescopes, as you might imagine. And then there's the Event Horizon telescope, which, even though it's not a space telescope, I have to bring it up, although it kind of is a space telescope, honestly. So this telescope was a combination of radio telescopes all around the entire world, and this created a telescope imaging system about the diameter of our planet. So you could say this is a space telescope the size of a planet. And this was the way that last year we were able to capture the first ever images of a black hole's event horizon. So this is a photo that was popping around last year that I'm sure I brought up during my live streams, and this is the first ever picture of it, or close-up picture of a black hole taken. And this black hole is actually in a separate galaxy, M87, which is a distant galaxy from our own. But this black hole is so massive that we were able to actually image it using this giant Earth-sized radio telescope. So very, very neat that we can basically create a telescope the size of a planet using those radio waves. All right, if you have any last minute comments or questions, be sure to put those in the comment section, because we are going to be starting to wrap up, and put those comments in now. But before we do finish up, while you're commenting or asking your last minute questions, I do want to bring up one other really cool activity that you can do that we can put a link to in the comments. And this is a fun activity to do with your kids at home, if you have any kids lying around at home. This is an activity that NASA has created. And it's from the James Webb Space Telescope page, and it is a build your own telescope activity, build your own space satellite activity. So this is pretty fun. So let's go ahead and launch this game here. This is a fun little activity that'll teach you a little bit more about telescopes, and let's just try it out here. So we'll just do a quick one here. Basically, what you do is, we'll just start on level 1 here, basic level. You basically pick what you want to study. So let's say I'm interested in studying exoplanets. I want to learn about planets around distant stars. That's going to tell me a little bit about the study of exoplanets. And then on the next step, it's going to ask us what wavelengths we want. And we'll see that it's actually limiting our wavelengths. So when we study exoplanets, we want to focus on infrared and optical light. The other wavelengths of light are less helpful for studying exoplanets. So let's pick optical light. And it'll tell us a little bit about some methods that telescopes have used to image exoplanets using optical light. And then on the next step, it'll ask us for a different type of sensor. So we only have one choice here, but in other cases, you may have multiple choices for different types of sensors. And this will tell us about the type of sensor, in our case, a camera for optical light. And then on the next step, it will ask us what type of optics we want to use. We'll use a single mirror. And then it will basically create a telescope for us, launch it into space, and then it will show us an example of what our telescope might look like. And our telescope might look like this, which looks a lot like the Kepler Space Telescope. And it will tell us a little bit about what the data our telescope produces might look like, and more information about that. So this is a really fun activity you can do at home. Again, we can put a link to that in the comment section, but this build your own telescope activity is a fun one you can try. And you can learn a little bit more about space telescopes, more than we had time to talk about during our live stream today. But it is time for us to wrap things up. And we got a couple people chiming in. Casey chimed in saying, sorry, I can't watch this week. Chiefs are on. Love space, just not much as the Chiefs. Hey, well, I love this Chiefs and space, so much so that I am currently monitoring the game right now. And it looks like the Chiefs have scored again. And we are up 6-0. Looks like we got another field goal. Pretty exciting, and the Patriots have the ball. So I am going to wrap up this live stream so I can get back to the game. But I hope you all enjoyed this stream all about space telescopes. And I hope You guys have a great week, start of your week for you all, and remember, you can come visit us at the Planetarium. We are open to the public if you feel comfortable. We are, of course, following many safety precautions where masks are required, and we are sanitizing the seats. So if you feel comfortable, we'd love for you to join us and see our live planetarium shows, or to visit Union Station and our other attractions like Science City. If not, though, I will catch you back here, same place, same time, 6 p.m. next Monday. I've got a fun plan for the rest of this month. It is October, so we're going to do some spooky live streams. Next week, next Monday, we will be talking about the infernos of the inner solar system. The planets Mercury and Venus and their, let's just say, pretty unpleasant landscape. So we'll talk a little bit about them and those pretty freaky places lurking right next door in our solar system. I've got a fun activity planned for later this month where we will be celebrating the first official crewed mission of the SpaceX Dragon capsule. We had the demo mission earlier this year, which we covered during our live streams, but the first official crew mission, where 4 astronauts will be sent to space, will be taking place at the end of this month. So we'll celebrate by talking about the International Space Station. I've got a fun surprise for that live stream. Should be fun. And then at the end of this month, I'm planning on doing a spooky live stream all about space mysteries. And I don't want to spoil too much about it, but we will be having a little bit of fun with that live stream. And it might remind you of a certain classic spooky sci-fi series. So be sure to tune in for all of those fun live streams for the rest of this month. I'll be seeing you same place, same time every Monday at 6 p.m. Once again, I have been your tour guide and planetarium specialist, Patrick Hess. Thanks for tuning in to another Planetarium live stream. Go Chiefs, and have a wonderful week. Bye, everybody.